Steinhauer here. Welcome back. We're now going to see how light can tell us the information about the temperatures of objects, how hot they are. And this too is something that you have some experience with in your everyday life. If you've ever cooked with an electric stove, especially one of those that has the metal coil, you've seen this process in action. So what happens? You start with a cold stove. It actually will look something like this poker here that's very cold. It looks just black. It isn't glowing. It's just sitting there. It may be reflecting some light from the overhead lights, but it's not glowing at all, and it's just sitting there as black. As you heat that thing up, though, what happens to it? You'll notice it starts to glow. And the hotter it gets, as you see here, the brighter it gets. And there's another thing that happens. If you notice, the color will change as well. If you start this thing out, just as it starts glowing, it'll be a very, very red color. And as you get it hotter and hotter, you'll notice it start to change to orange. And if you get it really hot, it'll start to be glowing yellowish and even whitish hot. And so the hotter you get it, the brighter an object gets, and it changes color as well from red to something that's not red. And so this is something that we can take to stars too and learn about the temperatures of things based on how bright they are, how luminous they are, and about what their color is as well. So, and this all comes from thermal radiation. We mentioned this in one of the previous videos when I was talking about continuous spectra, right? Every object in the universe that has some solidity to it and has some non-zero temperature, and by that I mean every object in the universe emits light, emits thermal radiation, right? We'll talk about what temperature is in a bit, but it is the random motions of particles, of atoms that make it up. And that random motion, because there are charged particles even there, even if the atom is neutral, you've got an electron moving around, and you've got a proton moving around, and that motion, as the object vibrates due to its temperature, will emit light. And that light will be at random frequencies, since the vibration will be at random frequencies. Not random, but it will be at all kinds of frequencies. And so all objects glow at some level. Now, the interesting thing about it is that the way that object glows, at least for a perfect radiator, depends nothing on what that object is made of. It could be made of hydrogen, it could be made of oxygen, it could be made of neon, it could be made of iron. The composition of that thing doesn't matter. The only thing that the spectrum of light that you get out depends on, we're talking about the continuous spectrum, is the temperature of that object. And so using that information, we can use that to get temperatures of objects just by looking at the distribution of thermal radiation. Here's an example. So we've got three objects here at different temperatures. One of them is actually four different temperatures. One of them is a 3000 Kelvin star, a cool star. We'll talk about what this means in a minute. One of them is the sun, a middle brightness star, a middle temperature star, and one of them is a very hot star, much, much hotter than the sun. And for scale, we've got people down here as well, because I did say every object emits light. We are no exception. We are constantly radiating light away. It's just that we can't see the light that each other give off. If we had light, if we had eyes, receptors that were sensitive to light in the 10 micron range, then we would be able to see each other glowing at night. But since our visible part of the spectrum, the part that we can see is here, we don't emit in that particular wavelength, and so we can't see each other glow. It takes much hotter things to be able to see those things actually glow. Okay, so two things though happen. As you increase an object, and this shows it very nicely, you'll see the two things that we talked about before happen. One is the brightness increases. How is that represented here? Well, the brightness is the area under this curve is showing you the total total energy being given off by this object per second. So as objects get brighter, as objects gets hotter, they get brighter. And not only do they get brighter at all wavelengths, right? So here is a 3,000 degree star, and here is a much hotter star. The hotter star is brighter than the cooler star at all wavelengths. Okay, that's one thing. The other thing that happens is you'll see the peak wavelength, the wavelength at which most of the light comes out. The mode of this distribution, if you know your statistics, moves and changes as you increase an object's temperature. And in fact, it goes towards shorter wavelengths or higher energy. As you increase an object's temperature, it goes from a peak at 10 to the 4 nanometers to 10 to the 3 nanometers for a cool star, to the sun, which is even less than that, to a much hotter star, which is peaking out here in the ultraviolet. So two things happen. Stars get brighter as you make them hotter, and the peak wavelength, the wavelength at which this distribution reaches its maximum, moves towards shorter wavelengths. Okay, we can codify this in a law, and the law is Wien's law. Wien was a German scientist, so we don't pronounce it Wien's law, we pronounce it Wien's law because that's how he pronounced his name. But this is there's a very linear relationship between the temperature of an object and where this distribution actually reaches its maximum point. And that's codified in Wien's law. And this Wien's law says the lambda max is the wavelength of the maximum intensity of the object, of the star, of the planet, anything that has a characteristic shape like that. And this number is and this equation is a number divided by t on the other side. This is a little confusing sometimes. Usually we'll have a constant here, but this is just a constant, 2.9 times 10 to the 6, and it has units of nanometers times Kelvin. So these aren't variables. This is a single number with units, nanometers Kelvin. Divide that by the temperature, and you get the peak wavelength of that particular object. So this works pretty well, right? You get wavelength in nanometers, as we were saying, and this codifies what we were saying before. If you increase the temperature, since temperature is in the denominator, you will decrease the wavelength at which this peak comes to this distribution comes to a maximum. Okay, the temperature has to be given in a particular unit though, and that is in kelvins. And if you're not familiar with kelvins, let's take a brief step back and talk about temperature scales. So we're familiar in the US at least with the Fahrenheit scale. The Fahrenheit scale is defined such that water freezes at 32 degrees and boils at 212 degrees. In fact, that is now how the Fahrenheit scale is defined. It's a useful scale because the normal range of temperatures that we are in contact with ranges from 0 to 100, and that's a useful range of numbers for us to be able to process and understand. The Celsius scale is similar. It defines its two points at freezing point of water and boiling point of water, but it sets them to be 0 and 100 respectively. Now the Kelvin scale, the problem with both the Fahrenheit and the Celsius scale is that when they were developed, they did not know, nobody knew that there was an absolute zero, which is why you have to have a 2-point scale. Most scales that we use have a single point scale because 0 is 0. If we're measuring distances, 0 meters is 0 meters. And that is one of the reference points of the scale. There is a 0 point for temperature, and it is neither 0 degrees Fahrenheit or 0 degrees Celsius. We talked about temperature as the motion of objects vibrating in a lattice or in a liquid or whatever it is, the vibrating motions of the particles that make up that object. Absolute zero, there is a thing called absolute zero. And as you make an object colder and colder, the motion gets slower and slower. Those particles that make up that object get slower and slower. And at the point at which all thermal motion stops altogether, those vibrations are 0, that is absolute zero. And so the Kelvin scale is a real scale in that it has its 0 point at absolute zero. This, by the way, is why you have to say degrees Fahrenheit and degrees Celsius. Fahrenheit isn't a thing because you don't start at zero. But Kelvin, which starts at zero, is a thing. And so you don't have to say degrees Kelvin. You can just say kelvins because it's a real unit, like meters is a real unit and seconds is a real unit. Okay, so Kelvin scale is set up nicely so that zero is actually at zero, but it keeps the same scale as the Celsius scale. In other words, there's still 100 kelvins between the freezing point and the boiling point of water. And since the freezing point of water is 273 kelvins, that means that the boiling point of water happens at 373 Kelvin. So this actually sets up the difference between the Kelvin scale and the Celsius scale. It's simply offset by 273 degrees. So absolute zero on the Celsius scale would be negative 273 degrees Celsius. But you should, for this class, never think about Fahrenheit and Celsius again. Kelvin is always what you have to plug in for every temperature equation that we will ever write down this semester. And we will be thinking about kelvins also as we go along. So it's useful to get used to them now. Okay, let's do an example. What is the peak wavelength of emission for the sun? Let's say the temperature of the sun is about 5,800 Kelvin. We switch to black. We know that the peak wavelength, 2.9, I've written it there. Let me write it again. 2.9 times 10 to the 6 nanometers times Kelvin. And I need to divide this by T, plugging in T, 2.9 times 10 to the 6 nanometers times Kelvin, divided by 5,800 Kelvin. Kelvins will cancel out. If I divide these two numbers, it actually comes out to a very nice round number. And that number is 500. And my units left over, the kelvins have canceled out. I only have nanometers left. So this is 500 nanometers. Does that mean that all of the light from the sun comes out with wavelengths of 500 nanometers? No, definitively not. Remember, this is a whole distribution of light. Let me go back to this picture, right? What that tells us is where this peak happens, where the most number of photons are coming out and what their wavelength is. But if you look, the sun is emitting light at all of these wavelengths. It's just emitting most of them at almost exactly 500 nanometers. Interestingly, 500 nanometers is in the visible part of the spectrum, right? Remember, the visible part of the spectrum goes from about 400 nanometers to about 700 nanometers. And this is not a coincidence. Our eyes have evolved to see the light that is bouncing around most regularly around the Earth. And that makes it easiest to see things. So in fact, this is in the green part of the spectrum, which is interesting. And it's telling that the sun doesn't look green. If the sun were emitting all of its wavelengths at 500 nanometers, it would look green. But because it's emitting also lots of red and blue and yellow and orange as well, our eyes synthesize all of those colors coming together as kind of a yellowish hue. And so that's the sun. How about for a hotter star? Vega emits with a peak wavelength of 290 nanometers. What is its temperature? We can turn this equation around. In fact, I want you to do this. Solve this equation. What is Vega's temperature if it has a peak wavelength of its distribution of 290 nanometers? Go ahead and solve it, and I'll come back and we'll solve it together after you're done. Welcome back. Let's do this. We need to do some algebra. If we take this equation and multiply by t on both sides, the t's over here will cancel out. And we need t by itself on top over here. We also need to divide both sides by lambda max. And the lambda maxes over here will cancel out. And we'll get an equation that looks like t equals 2.9 times 10 to the 6 nanometers times kelvins divided by lambda max. And since I know that lambda max is 290, let me just plug in 290, 290 nanometers. Take 2.9 times 10 to the 6 and divide it by 290, and you're going to get a number that is 10,000. And what are the units? We've got nanometers canceling with nanometers, and the only unit left are these kelvins. So the unit on this number is going to be kelvins. And so a temperature, the Vega has a 290 nanometer. Vega is a bright star in the summer sky and summer triangle and constellation Lyra. Wavelength peak at 290, hotter than the sun. You know that because this is a smaller wavelength than the sun emits at. And in fact, it's 10,000 Kelvin instead of about 5,800 Kelvin, which is where the sun is. What part of the spectrum is this in, by the way? 290 nanometers. Again, the visible part of the spectrum ends at about 400 nanometers. This is shorter of that. This is in the ultraviolet part of the spectrum. Okay, here's one more question for you. And that is, which is hotter? A red star, a blue star, or a planet that emits only infrared light? What do you think? This is kind of counterintuitive. We think of, well, let's say the answer, right? And let's actually go back to this diagram, which I think will make it more clear. Look at this hot object. We've already colored it blue. Why is it blue? Well, it's peaking out here in the ultraviolet, but look through the visible part of the spectrum, it's much brighter at the blue end than it is at the red end. This star will appear much more blue than red because we're getting a lot more blue light from it than red light. Here's a cool star, and you see the peak is in the infrared, but it's exactly the opposite through the visible part of the spectrum. It's bright at the red end and dim at the blue end. This object should look rather red in the sky. And in fact, you can go and see that. If you go out in a clear night in the wintertime, the constellation Orion will be right out there for you. And you'll see the head of Orion is Betelgeuse, and it's a very red star. And the foot of Orion, directly on the other side of the belt, is Rigel, and it's a rather blue star. If you're at a dark site, you can actually quite clearly make out the difference in color between these two stars. And it must be the case that the blue star is quite a bit hotter than the red star. The color is physically telling you what temperature those objects are, which is kind of counterintuitive. We think of blue as a cool color and red as a hot color, but in the world of thermal radiation, cool objects are red and hotter objects are much more blue. The answer to this question, the blue star would have to be a lot hotter. Maybe I'll make a blue star so that it's more obvious. Okay, one more topic in this particular section, and that is, we've quantified how the wavelength changes as an object's temperature changes. How does the luminosity or brightness of that object change as we change the temperature? And that's this law. L equals A sigma T to the fourth. So let's write these equations down, define these terms, and we'll tell what we're talking about. L is a word that you've probably heard before called luminosity. I've used it before, maybe even in this video. Luminosity is the intrinsic brightness of an object. It is how much energy, it is energy per second. Energy per time, really, or joules per second if you'd like to use our normal units. So it's how much energy an object is giving off per unit. A is the surface area of that object. And since we're always talking about stars, well, not always talking about stars, but we're in astronomy in this class anyway, we'll basically be talking about spherical objects. And the surface area of a sphere is 4 pi times the radius of that sphere squared. So you'll often see this written 4 pi r squared sigma T to the fourth instead. T, of course, is the temperature. And sigma, I'm going to write it down. It's a constant. It's just a number. It has a name called the Stefan Boltzmann constant. And you can look it up. It's 5.67 times 10 to the negative 8. And it's got weird units of joules per seconds times meters squared times Kelvin to the 4th power. So this codifies what we saw before, in that if you make an object hotter, if you increase its temperature, it's getting bright. And this is a very powerful equation because of this 4 here. Raising the temperature by a little bit or lowering it by a little bit affects the luminosity a lot because you're raising that number to the 4th power. I'm gonna actually codify and write this down. This is equivalent to, for spheres, 4 pi times the radius of that sphere squared times sigma t to the 4th. So you'll see this written both ways. Sometimes you'll be given a radius, and if you are, this equation will be more useful to you. Okay, one more question for you. If you double the temperature of an object, by how much will its luminosity increase? Go ahead and give it a go. Okay, so let's answer this question together now. We know that L equals 4 pi r squared sigma t to the 4th, right? So if we increase the temperature of an object, we are only increasing the temperature. We are leaving all of this other stuff constant. We're not changing 4 and pi or sigma, those are constants. But if we leave the radius of an object, the size of an object the same, and we just increase the temperature, how does doubling the temperature change the luminosity of an object? The answer is, if you double the temperature, you have to increase the luminosity by a factor of that factor to the 4th power. So if you're comfortable with that, that's okay. But really what we're asking here is a ratio of an object with a certain temperature and an object with a temperature that is double that, right? So we can say, let's actually do this explicitly. L1 and T1 divided by L2, 4 pi r squared, sigma T2 to the 4th power, right? So L1 over L2 is how much brighter that is. This is what we're asking. By how much will its luminosity increase? I'm usually asking what factor, and that's just taking a ratio, L1 over L2. Well, that's pretty simple to do now. We can say 4 pi r squared, sigma T1 to the 4th, divided by 4 pi r squared, sigma T2 to the 4th power. And the cool thing is everything that hasn't changed, this 4 pi, this r squared, oh, I didn't put an I squared, but it is, and r squared down here. R squareds cancel out, the sigmas cancel out, and the only thing that matters is the thing that's changing, and that's the temperature. And if we double the temperature, well, let's actually do a little bit more algebra. We can say this is T1 over T2, T1 to the 4th over T2 to the 4th. I can rewrite this as, let's take the ratio first and then raise it to the 4th power. Those are equivalent things. And I know what this ratio is. If object 1 is double the temperature of object 2, then this is just a 2 to the 4th power. So taking ratios of things make it so that you can see how changing a single variable will affect that parameter on the other side. And so in this particular case, doubling the temperature, in this particular case, doubling the temperature will lead to a luminosity change that is that factor of 2 to the 4th power. And in this case, 2 to the 4th power is, what is 2 to the 4th power? It's 2 times 2 times 2 times 2, 4 times, or 16, right? If you double the temperature of an object, its luminosity has to go up by a factor of 16 to compensate. That's fun. If you triple the object's temperature, it will go up by a factor of 3 to the 4th power, which is even bigger. The other thing to notice and important is temperature is an important object, obviously very important for the luminosity of an object, but so is radius. If you have two objects that are the same temperature, the bigger one will be far more luminous than the smaller one. So both an object size and its temperature will relate to how intrinsically bright, how luminous that object is. Okay, we'll talk about luminosity and how it's related to brightness and how bright objects appear in the next video. So stay tuned.